Rain gardens and bioretention swales are the most efficient way of managing your stormwater. Soils, plants, and trees work together to provide a source control for stormwater. This works fine in rural and suburban areas. However, it is much more expensive in dense urban settings where land is too expensive to give away to rain gardens and bioretention swales. They collect garbage and have much higher maintenance costs. I want to explain a little bit about how bioretention works, as it will impact on our discussions about suspended pavement systems. The soil in the bioretention swale is uncompacted. The soil should have structure. So the structure provides these micro and macro pores, which is where we hold the water in the soil column. The difference between the field capacity and the wilt point is the 20% holding capacity for water in the soil column. So what's so important about soil? Ironically, trees are not very good at absorbing resources from the soil because for 400 million years they've been living in a symbiotic relationship with bacterial, microbial, and fungal networks in the soil column. So how does this work, and how is it relevant to stormwater? The fungal networks provide reach or transport. If we look at the surface area of the tree roots and the mass of tree above grade, the physics doesn't work. There's not enough surface area on the roots to absorb enough nutrients to support the tree. The fungal networks provide hundreds of thousands of times more surface area to pick up nutrients. So the microbial life breaks down the carbon-based pollutants to make them bioavailable to the tree. The fungal networks absorb these nutrients and metals, and the fungal networks also bring the phosphorus and nitrogen directly into the tree root cells. The tree root also provides a surface. The trees provide carbohydrates and sugars to the fungal and microbial communities, which is their source of energy. And water is what ties this virtual circle together. It provides transportation. Water molecules transport the nutrients from the soil through the fungal network into the tree roots and up the trunk into the canopy, where they're used in photosynthesis. The water molecules drop their nutrient loads and are expelled into the atmosphere through the stomata of the leaves. Only about 10% of the water that a tree uptakes is used in photosynthesis. Fully 90% of the water that a tree uptakes is used for transport. So this is the process of evapotranspiration. So we have always known that trees are a significant source of evapotranspiration. Now we have evapotranspiration calculators that are peer-reviewed and have been accepted by stormwater regulatory agencies. This is, for example, a model that we did for the City of Toronto on a standard 90-meter street, and we looked at the 8-inch diameter trees with the appropriate soil volume on those on that street and how much water it would evapotranspirate. So the model shows us that 8-inch diameter trees will evapotranspirate the 5-millimeter rain event in the 3 days after that event. And then at maturity, these trees will evapotranspirate the 13-millimeter rain event in the 3 days after this event. So this is significant excess capacity that the trees bring. So now that we have discussed bioretention and evapotranspiration, let's get back to the topic at hand, suspended pavement systems. A suspended pavement system is made up of a structure that will support a loaded surface, sidewalks, plazas, parking lots, and provide a void space to store soil, water, or both. And generally, suspended pavement systems come in two types, gray or green. So the gray infrastructure usually comes in the form of cisterns. Example, stormwater boxes, chambers, or clear crush aggregate fields. So here we have the water from the roof leaders and the surface flows all flowing into catch basins. The sump in the catch basin is capturing the initial TSS, and then the water is stored in chambers, stormwater boxes, or clear stone cisterns. If you want to do quality in these systems, then you need to provide a mechanical filter. For example, oil grit separators, storm scepters. And there is always an ongoing maintenance cost associated to maintain these filters and clean out the cisterns. Green infrastructure suspended pavement systems come in different forms as well. However, they all apply bioretention technology that we discussed earlier under a structure. This is the City of Toronto's precast soil trench, for example. So here we have precast slabs that bridge over the uncompacted soil underneath the sidewalk, and we now are able to capture the surface water from a sidewalk or plaza through a trench drain, run that water into the soil volume below, and the soil volume is doing stormwater services, so retention, detention, and cleaning the water, as well as supporting large mature trees. This is the Skyforest in Japan, which is a very expensive suspended pavement or vaulted pavement system. Here they're using sonotubes filled with cement, and the plaza is floated over top of these pillars. So we were managing all of the water in the plaza through soil and the trees as a source control. Soil cells are an alternate green infrastructure way of managing your water as a source control. These are modular structures that support the sidewalk, car park, or plaza, and the surface water is captured from the streets, sidewalk, disconnected roof leaders, and brought into the soil volume where you can do retention, detention, and clean the water of pollutants. Then either there is ground recharge back to the aquifer, evapotranspiration, or water is returned to the stormwater system much later, reducing peak flows. This is a demonstration project that we did with the City of Toronto and Toronto Water back in 2008. The catchment area is one end of the block to the other, and from the crown of the street to the building face. And all of the water is going into 2 silva-cell trenches. So the water comes into the catch basin as it normally would, and the sump captures the initial TSS, total suspended solids, and then we set a pipe just above the sump which brings that water into the soil cell trench. And we match the design storm to the volume of soil cells or soil necessary to manage that design storm event. The larger rain events saturate the soil cells, fill up the CB, and it backs up into an overflow pipe. So this water would then go directly to the storm system. So here's one of the soil cell trenches, and we have a drain line at the bottom, which is connected to the downstream CB, and then we fill the silva cells with soil. So here we have water coming into the CB off the street as it normally would, and then this black pipe set just above the sump brings the water into the soil cell area and connects to the 8-inch perforated pipe that is distributing that water through the whole soil column, through the silva cell trench. We have a drain line at the bottom. Also, if your site had ground recharge, then you could also get ground recharge and storage as that water goes back to the aquifer. There's cleanouts on all of the distribution pipes and the drain lines. So this is the only maintenance on this system is cleaning out the CBs and the TSS in your sumps. You can also blow out your distribution pipes back into the CB to capture any TSS that might have been resuspended and got into your distribution lines. So there's no need for oil grit separators, there's no need for storm scepters, and there's no need for cisterns, and the maintenance associated with these systems. And we have 2 trees planted in each of the trenches, and as we talked about before, the trees are an integral part of the system. The trees not only are providing evapotranspiration and adding to the storage capability of the system, but through this symbiotic relationship with microbial life in the soils that we talked about, these trees are feeding those microbial communities with sugars and carbohydrates and keeping those communities healthy. Those communities are doing all of the cleaning work in terms of taking up the phosphorus and nitrogen. So the trees are an integral part of the system. They are, in fact, bioutilities. Then we build a deck at the surface, and build your sidewalk and parking lay-by on top of that. So now we have, unlike a cistern that would just hold your water, we are cleaning this water. So we're taking 93, 99, 98% of all the metals out, 73% of the phosphorus, and 60% of the nitrogen. So all of the things that we talked about before in terms of how a bioretention swale and the soil and the trees work in a bioretention swale, we're applying that technology, but we've just built a roof over top, and we're able to apply that technology as a source control. So now we've integrated soil, trees, and rainwater in a one integrated system. So this is a more commercial site that might be more relevant in Mississauga and some of the applications that you would do in Mississauga. Here, water is brought to the porous pavers above the parking bays from the roof leader disconnections, and the asphalt is graded to the parking bays. You could either use cisterns or soil cells below the parking bays to do peak flow reduction, storage, and water quality. So here in a gray suspended pavement system application, you'd have cisterns and oil grit separators with the associated maintenance cost for changing filters. And with the green suspended pavement systems, we use soil and trees, and the only maintenance is cleaning out your catch basins and sumps, or cleaning the porous pavers above to remove the TSS. So here we have an efficient use of space. This design does not give away parking spots to soil volume islands. It doesn't give away parking spots to bioretention swales and rain gardens around the perimeter. And these systems are scalable. Here the suspended pavement system is replacing the stormwater pond. The developer was able to build 2 new buildings due to the space saved by not having to have a stormwater pond and the associated berms and setbacks required. So this is the silva cells that fill the central square. And we're using both the void space, an 8 to 12-inch void space at the top, and the aggregate field below to increase the storage capacity. And the soil in the middle of the silva cells supports the trees and provides the water quality. So we have an efficient use of space. This can be a parking lot during the week, farmers market on the weekend, so it becomes a programmable space. And so all of the water from the whole site is pumped into this central square. The perforated pipes distribute that water through the whole soil column, and then the soil is saturated, the aggregate field below gets saturated, and then the void space at the surface becomes a cistern, fills up with water, and we have also trees planted in the system. And as we spoke about, all of these systems have overflows, so as the water raises to the top of the silva cell decks, it reaches its design storm capacity, and then the overflow pipe picks that water up and takes that water to the storm system. So the advantages, some of the advantages of the suspended pavement systems. For the green suspended pavement systems, we have a reduction in maintenance costs. We have no filters to change or cisterns to clean. For both gray and green suspended pavement systems, there's no need to replace TSS matting or clean out garbage and replant daylighted bioretention swales. There is a much more efficient use of space for both gray and green suspended pavement systems. There's no loss of parking to bioretention swales, to rain gardens, and to soil volume islands. And an additional benefit of large mature trees in the green suspended pavement systems is added storage capacity, reduction of the heat island effect, aesthetic values, and increase in property values. There are challenges with suspended pavement systems. They do have higher capital costs than a daylighted bioretention swale or rain garden. Often these higher capital costs, though, are offset by the reduction in the maintenance costs over time. And there is more detailed design work needed to be done to implement the suspended pavement systems. So looking at the City of Mississauga's credit system, and we can see how the suspended pavement systems allows you to achieve these objectives. So in terms of peak flow reduction, both the gray and the green suspended pavement systems, so cisterns or soil cells, will allow you to meet the reduction for the 100-year post-development flow to pre-development conditions of the site. In terms of water quality, both systems will do water quality, whether it be through a mechanical filtration system or through the soil biology, and we can meet the provincial criteria for enhanced treatment. In terms of runoff volume and reduction, you can use ground recharge, evapotranspiration, reuse, storage. All of these features in both the gray and the green suspended pavement systems will allow you to reach these runoff volume reductions. However, these objectives are always going to be site-specific. So, for example, if your site doesn't have any ground recharge, then you're not going to be able to get that storage capacity if you just don't have it available through ground recharge. So all of these are going to be site-specific. In terms of pollution prevention, the suspended pavement systems are an integral part of a pollution prevention plan. For example, if you had an oil spill at your site, currently the water would hit the catch basin and the oil would hit the catch basin and run out through the whole municipal storm system. With the suspended pavement systems, you can always go to your downstream CV, close that off, and now you have kept all of the oil and the pollutants on site, and you can do your remediation plan and put into place your remediation plan without this running out into the whole municipal soil system, storm system. So if there are more questions with regard to suspended pavement systems and stormwater management, my contact information is here, and please feel free to reach out and ask questions. Also, you will find more information on DeepRoot.com, and also on DeepRoot.com, our blog, you will find a lot of scientific research relating to both stormwater management and the application of LID solutions. Thank you very much.